Good morning, folks. Can you hear me okay? Oh, you know what? Maybe you can't. I need to change something real quick on the share screen. Hold on a second. Okay. All right. People can hopefully see that and hear me okay. Can you hear me all right? Nobody can hear me? Good. See some thumbs up. Fantastic. Good morning. How are we doing today? Everyone simultaneously said great, awesome, cool, or so I assume. Good to have you all on this nice morning. I am here to chat a little bit about trajectory optimization. It's what we covered last class, okay? And we're going to code it all up from scratch. I'm excited. Hope you are too. We're going to do it from scratch. So let's pull up just a few quick course reminders, all right? Today, 2026, 02, 19 of the Common Era. Okay? We've got just a few reminders, okay, for class. There is a quiz. It's due 5 p.m. today up on Canvas. Just a reminder. You should have seen an announcement about it. It's up. I think there was one question that needed to be revised. It's been revised. If there's any other issues, please contact the TAs. They're able to respond more quickly than I am to make sure everything's good. So, all right. And so that's a Thursday today. And on Friday, I need your project proposals submitted. And that's up on Canvas too. So they're going to be up on it. So you only need to submit one per group and you're good. If there's any issues with group, contact the TA, okay, if you're not in a group, all right? So here's a question. All right. That's everything out of the way for courses at the moment. Homework 2, we're finishing up the details on it. Should be released soon. It's going to be on optimization, specifically the optimizations you've been doing on linear and quadratic programming. So it should be exciting. All right. But now, recall, we've done some optimization. And we've done some control. Now we're going to put them together for some optimal control. What we covered last time was lots of ways of combining optimal control, one of which was trajectory optimization. Okay, trajectory optimization was really cool. Remember, I was pulling up all those videos of the triple pendulum on a card swinging up. Yep, that's trajectory optimization in action. Other types too. So is a method of generating a feed forward trajectory for a dynamical system subject to minimizing a cost and satisfying constraints. Okay? That's the big picture there. All right? So that's what we're going to code up today. So it's going to require us to do a couple things. We're going to need on one hand, what will we need? We will need an optimizer or an optimization algorithm. And for that, we're going to use MATLAB's fmincon. Okay? That's what it's called in MATLAB. The actual name, the official name for the algorithms, it actually has many at its disposal. The one that's most likely to use are things like what we call interior point, or something called sequential quadratic programming, or SQP. It will often pick the one that's best for the problem, or you can tell it which one you want, okay? There's another one called active set, and a trust region reflective method. You can look up the different algorithms, the ones that fmincon has at its disposal. But the key is the fact is that it minimizes a function, that's your cost function, with respect to, while satisfying constraints, the con, okay? Right? We're going to need an optimization algorithm, and we're going to need a simulation of our dynamical system. Okay? And most importantly, we're going to need to set up the optimization problem ourselves. We have to define the optimization problem. And so much of this part of the course, and the course in general, is just setting up the optimization problem. And again, that's our decision vector. That is our cost function. Those are our constraints. Okay, that's what we're going to do today. But let's reintroduce the problem that we're going to be solving first. Really easy one, okay? Called it the drag race. You know, it's a car. Starts at rest. Ends, has to get from one point to the other really fast, okay? This is our problem. Drag race. There's our car. It's beautiful, gorgeous. I'm sure Elon will be selling it in a couple of years in that exact shape. Okay? There's a position of that car. We'll call it S of t. There, that's a car. Hopefully that's obvious by its very sleek shape. We'll be selling millions of units. All right. And we want it to finish here. Little dash line, happy little dash line. M at the end there. So it's going to be some S final or SF, okay? That's a car. And we're going to put a force on that car. We're going to call it U of t, right? So our goal is to stop at the finish line in minimum time. That's what we set up last time, okay? And subject to force limits. Okay? So let's set up our optimization problem, okay? Our optimization problem. Okay. We need our decision variables, okay? For our decision vector, call it W. I'm going to write it as a row vector, then transpose it. And I'm going to say it has a button U1, U2, all the way up through some UN. And UN. And I'm going to include the final time, TF. TF, that's an F. Question, Josh? Okay. So TF, that's our decision vector. Those are the things that the optimization is going to decide. Okay? Where we're going to define U of t as a spline where here is time. This is our final time TF. And then there's going to be a bunch of points along that spline. I'm just drawing them in arbitrary places just to show a little picture, right? Where they're evenly divided. And we'll have little linear connecting points between them, where this is U1, this is U2, all the way up through UN. So when we simulate, if we're at time 0, this is the force that would be being applied right there. Then as time moves forward, it increases until there, blah, 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 blah. But the optimization has control over U1, U2, all the way up through UN. And the final time. So if it makes the final time smaller, it scrunches the whole trajectory. If it makes the final time longer, it stretches the whole trajectory. Make sense? Any questions so far? This is what we set up last time. And that's just a linear spline. And all that does is it allows us to create decision variables, discrete decision variables, okay, that are real valued, and turn that into a function that we can call to be U of t for our trajectory, right? Okay. Now our cost function. Okay. Just for today, I'm going to call it J, capital J, because we're going to use F elsewhere. Okay. Cost function J of W. What's the thing we're trying to minimize for this problem? Well, minimize the time to get to the finish line. So our cost function is a function of our decision variables. Well, look. Hey, look, there's the decision variable right there, time, TF. Okay. Now our constraints. Okay. What are our constraints? Well, we have to finish at S final, and we want to have it come to rest. So here we have ST. So S at the final time, T final. S at times T final is going to equal S final, or SF, or whatever we're going to call it. And the time derivative, the velocity, S dot at T final, is going to be equal 0. Okay? These are equality constraints, as you can tell. That's some of my worst handwriting. Let's redo that. Constraints. It's marginally better, okay? And we have some limits on our force. So U of t is between some U max and some U min. Those are, of course, inequality constraints. Following along? Additionally, you could treat these as bounds, because literally they're just limits on a variable. So you can treat them as bounds when you're setting up the optimization. There's lots of ways you can write it into the code. You can treat it as just an inequality constraint. This is actually a linear inequality constraint. You can treat it as a nonlinear inequality constraint, even though it's linear. It's just a little, it's not as easy to deal with. Or you can treat it as a bound. Okay. So, hey, we did it. We set up the optimization problem. Great. How do we use that? How do we put that into MATLAB? So let's pull up MATLAB, friends, and let's get started, all right? So go over to MATLAB. Good old ye olde MATLAB, all right? So let's familiarize ourselves with some of the optimization tools. We've already used linprog for linear programming, okay? for when we have a linear program. That's a linear optimization problem with linear cost and linear constraints. We've used that, right? And you type help lin prog, it tells you how you can use it. You can give it a cost function, A and B. You can also give it inequality constraints through A and B, equality constraints through AEQ, BEQ, lower bounds and upper bounds, and additional optimization options, okay, which you can set through the optim options command. We used this before. We used that specifically also when we were doing quadratic programming using quadprog, okay? Quadprog. Now, the nice thing about MATLAB is that it says, oh, I have a quadratic programming problem. It will then use whatever optimization solver it needs to use, whatever algorithm, okay, whether it's interior point or what, you know. Excuse me. Okay, so, and you can see it's very similar, right? We had to define a cost function. In this case, it was defined using the Hessian and the gradient. We have our inequality constraints. We have our equality constraints, our bounds. If you want, you can give it an initial guess for what you think the answer is for all your decision variables, x0. You notice that it calls the decision vector x, whereas we call it w, I think. Did we call it w? Yes, we did. Thank goodness. That's an old habit. I used to call it x. And that becomes a problem when we have state vectors x, right? So that's why we use w. You set options, right? Seeing a pattern here, how you set these things up? Now, what we're going to be dealing with is not a linear program, not a quadratic program, but because we have actually some nonlinear constraints, it might not be super clear as to why it is, but nonlinear, but they are nonlinear. We're running through a big integral. A whole simulation is being run in our constraints. We're going to have to use fmincon, which is not a nonlinear solver. Okay? So you can see it's very similar, okay? fmincon, you have to give it a function. That is your cost function. But it can actually be a whole MATLAB function. It could be a whole file, right? That takes in your decision variables. Here we go. That takes in your decision variables, W, as we call it, right? And returns the cost. It can be an entire function. It could be an entire simulation, right? That's executed inside that function. Just like when we're using ODE45, we have to define a dynamics function, and it could be like a literal MATLAB function with inputs and outputs. Same thing here with this cost function, all right? In fact, it says function to minimize. It's a function handle. You give it a function name, just like ODE45, all right? Then you have to give it x0. That is your initial guess. It calls it the initial point. It's a vector of real numbers. So for every decision variable that you have to give it an initial guess. Does that guess matter? Yes, it does. But in certain problems, it matters more than others, okay? Sometimes you can get away with a really terrible guess, and sometimes you can't. For single shooting, it tends to be a little more sensitive to the choice in initial guess. You generally speaking want the guess to be better. I think I'm giving you a pretty simple problem where you can give it a pretty bad guess, and it works, okay? But we're in the realm of nonlinear optimization. So a lot of the guarantees that we have that we're going to come up with a local minimum, or even especially not a global minimum, are out the window. Okay, it's probably not a convex problem. Okay, but again, you have your A and your B matrices. Those are for your inequality constraints. AX is less than or equal to B. Your AEQ and BEQ for your equality constraints. Lower bounds, upper bounds, and this here, non-LCON. It's another function, a function handle, just like with the cost function, all right? So, well, how does it work? It is a function handle that returns the value, the constraint violation of your inequality and equality constraints. Specifically, what I'm talking about, let me pull it up here, back on the screen. Okay. Specifically, what it's looking for, it wants G of W is less than or equal to 0, and it's asking for G of W, and it wants to know GEQ of W is equal to 0, excuse me. And it wants to know GEQ. So non-LCON, that's what non-LCON returns. So what you're going to want is you're going to want create a function that returns G, and GEQ is equal to non-LCON of W of your control of your decision variables, right? And your cost function, so those are these are your nonlinear constraints. Nonlinear constraints. Okay? For your cost function, it's very similar, right? Your cost function, you're going to return the cost, okay? It's going to be equal to some function of W, right? So you can create function handles in that format, okay? That's what we're going to do. So before we do this for the drag race problem, let's do another quick example, okay? Okay? Remember the fencing problem? Remember that? Where we have some length and some height of a fence that you want to maximize. You want to maximize A. Let's write that up really quick because it's a much simpler problem and have fmincon solve it, okay? Where our decision vector W was our length and our height. Our cost function, so J of W was equal to our area, but we want it to be minus our area because we want to maximize. It maximizes area. And we had a perimeter limit where we wanted to say that 2L plus 2W plus 2H was less than or equal to 40. Okay? It's a perimeter limit. Okay. So if we wanted to turn this into a GEQ is less than or equal to 0, or GW of less than or equal to 0, that would mean that 2L plus 2H minus 40 is less than or equal to 0. And this here, my friends, that's going to be G of W. Okay? So if we want to write this up as a MATLAB function, let's go back to our code. Let's create a new script. Okay? Let's call this one solve fencing.m. Okay? By Christian Hubicki. That's me. Can we see this okay? Is this big enough? I can make it bigger if necessary, but hopefully it's coming through on the share screen on Zoom and you can see it okay on YouTube. All right. Cool. Christian Hubicki and friends, that's you. All right. Today, 2026, 02, 19 of the Common Era, and we're going to solve the maximum area of a rectangular fence using fmincon. Okay? So first thing I'm going to do is I'm going to clear everything. CLC, clear, close all. Clears the window, clears all the variables, closes all the plots. Okay? Now, I need to be able to run fmincon. So what am I going to need? So I'm going to need the three things. I need to define what is fmincon asking for. Excuse me. Where's my mouse? It's somewhere in this world. Where did it go? I think my mouse died. Excuse me, friends. I'm going to plug it in. There we go. I think that did it. Gotta plug in my mouse. How about that? Ran out of batteries. So we're back in action. So we've got that. We got it clear. So for fmin, we want to use fmincon to find the maximum area. And if we go to here, what does fmincon need? Fmincon is going to need a cost function. Okay, it's going to need an initial guess, an A and a B matrix if we have linear inequality constraints, and linear equality constraints, upper bounds, lower bounds, and non-LCON. We're going to intentionally put our constraints as non-linear constraints, even though we could write them as linear ones, just to show how you would use the non-LCON, okay? So let's define things. Well, we're going to define our function, okay? So our cost function, let's just call it cost, is going to be a function that takes in our decision variables W, okay? So if it takes in a decision vector with W here, which the first element is L, the second element is H, it's going to be minus the first element times the second element. So it's going to be minus the first element, so it's be W1 times W2. There you go. That's our cost function. Okay, in a cost handle. I'm going to put a little semicolon so we don't have the little warning. Done. Okay. What else do we need? We need x0. That's an initial guess. We'll call it W0 because we're calling our decision vector W and not X. All right. And let's just guess 5 and 5. I don't think it matters if it's a column or a row vector. I think it knows what to do with it. But either way, I'm making it a column vector. This is our initial guess for L and W. So L and H, sorry. All right. All right, so L and W, let's see what happens. Now, we can ask for linear inequality constraints, linear equality constraints, but we can ignore those, okay? So what we could write is that for A, we can just make it open close bracket. B is open close bracket. AEQ is open close bracket. Empty vectors. BEQ is open close bracket. LB and UB we'll get back to, but we'll say it's open close bracket. That just tells the optimization these don't exist, so it just ignores them, right? But then we need non-LCON, okay? All right, I'm going to make this, let me save, by the way. I'm going to save this as, what do we call this? Solve fencing.m. Let's see, single shooting range optimization. Here we go. Good. Everything making sense so far? So I'm going to make a whole new function file for non-LCON, just to show you how you might do this, because we're going to need to do this in the next part of the problem for the trajectory optimization. Made a whole new function file. So I'm going to say function, okay? And this function has to return two things for non-LCON. Where's non-LCON here? Here we go. Right there. It's going to return G and GEQ for a given W. So it's going to return G, that's a Q, G for inequality nonlinear constraints, GEQ for equality nonlinear constraints. Non-LCON is the name of the function. We'll call it non-LCON fencing because we're going to have multiple non-LCONs in this folder. Okay, you can call it whatever you want as long as you tell the optimization what the function is, right? And it takes in our decision vector W, okay? So it returns our values of the inequality and equality constraints respectively. when given a value of W. Okay, our decision vector. Okay, and to know what's going on here, keep in mind that W1, as we called it, where is it? Our first element of W is what we call L. Let's write this out explicitly. We don't have to do this, but let's say L is equal to W1, right? We could say that H is equal to W2, right? Now our there here, right there, there's our inequality constraint G of W. So G is going to be equal to 2 times L plus 2 times H minus 40. Done. Now, we don't have any equality constraints, but if you did, you would set them equal to whatever you would solve them to be. But so you don't have them, we just return an open close bracket, right? So no constraint. You should return an empty vector, right? And if you had multiple inequality constraints, which we might add, right, you would put them as a vector with multiple rows, right? That's it. So we don't need the bracket because we only have one. And say to return a column vector with all the constraint violations. Meaning how off are we with the constraints, right? Make sense? Let me make sure you can see that. Okay, let me get rid of that. I want to follow what I've written. Okay. That's non-LCON fencing. Okay. I saved it. It's now I'm going to save this non-LCON fencing as an own function file. It's in the same folder as solve fencing. So let's go to solvefencing.m. Okay. We're going to now run our optimization using fmincon. So we're going to say our optimal decision vector, W star, keeping in mind we like to write things like this. We like to write our, keep in mind we write our optimizations like this. Let me pull this up in bigger. So recall our general nonlinear program. Where W star is equal to argmin W, J of W. We're just writing it as J because we'll see F elsewhere in our problem today. Subject to the constraint or such that G of W is less than or equal to 0, and GEQ of W, if you have equality constraints, is equal to 0, right? That's what we just written out, right? So back to our code here. So W star, our optimal decision vector, is equal to fmincon. We want to give it our cost function. It is a function handle here called cost. It's already a function handle because we gave it the little at already. So we just say cost, okay? Now we give it x0 or w0, which is our initial guess, w0, sort of hinting us what we need. Now we need A and B, AQ and BEQ. Well, I've already defined them as empty vectors here. A, B, AQ, BEQ. Then our lower bounds and upper bounds, LB and UB. And non-LCON, these are our nonlinear constraints. We defined it in a function we called non-LCON fencing, but it's not currently a function handle. Because if I just typed non-LCON fencing underscore, it would think this is a variable called non-LCON fencing. But because we haven't already called it a function handle with this little at, we got to tell it it's a functional handle by saying at the beginning. So at non-LCON fencing. Options we can add in a minute, okay? So let's just run this without the semicolon and see what happens, see if we get any errors, okay? Done. Anyone getting that? Anyone get that? Thumbs up. I see some thumbs up. Great, right? Hey, what's being returned? The value of W star, the optimal decision variable, this decision vector, right? It says local minimum. First thing you want to check. First thing you want to check whenever you run any of these optimizations, what is the output here for did it solve, right? There's no guarantee that it worked, okay? Local minimum found that satisfies the constraints. That means it worked. Great. Okay, local minimum found. Oh, music to your ears. You should listen and hear that singing in your brain. It's like, oh, like a dopamine hit. It worked. Okay, meaning it solved whatever problem you gave it. Now, if you gave it the wrong problem, that's on you. It's entirely possible you give it the wrong problem that it solves. But whatever problem you gave it, it solved. And it gave you 10 and 10. That's the right answer to the fencing problem, right? It's a square. It's a square, and it's going to be 10 on a side. 10, 20, 30, 40. Uses all the area. Perfect. Great. Awesome. Neat. Cool. All right. So that's how you use fmincon. Now, we did choose the initial guess to be 5 and 5. I just arbitrarily chose that. I'm going to try choosing 0 and 0. I want to see what happens as my initial guess right there. 0 and 0. Going to run it again. All right. What does it say? It says initial point is a local minimum that satisfies the constraints. Meaning that I gave it a local minimum. What did it tell me the answer is? 0, 0. What? We know we can do better than that. But it's a local minimum, right? Not a global minimum. So the initial guess we started it out at it was at 0, 0. The gradient at 0, 0 is flat. It's 0. So if it's using gradient descent, which all of these algorithms we're using use some kind of gradient descent where it's trying to move down a gradient, the gradient's flat. So it's stopping. Okay? So did the initial guess matter? Yes, it did. Okay? Keep that in mind. Let's try a different initial guess. Let's try -1, -1. All right? And rerun it. Problem appears unbounded. Interesting. What did it find? -70 billion. -70 billion. What? We ran into this problem before, right? If we, when we did the fencing problem, because we didn't tell it a negative length was impossible, and we told it, hey, try, and we told it, hey, try a slightly negative value to start with for your initial guess. It just kept it making it more negative. If this value is negative, and that value is negative, this becomes positive, and then you negative it again, that's a really low number. So we have to tell it that we don't want the values to go negative. Now we can do that with a lower bound and an upper bound. Okay, and this might help us out. So let's try our lower bound. We have to set a lower bound of 0 for both of those values, 0 and 0 right here. So this sets the lower bound. And if we have no upper bound that we want to tell it right now, we can say infinity, infinity. Okay? Now if we run that, and voila. It knows that negative is bad. Well, first thing we got to check, local minimum found that satisfies the constraints. Awesome, cool. It found at least a local minimum. Might not be a global minimum, but a local, 10 and 10. We used non-alcon. We used fmincon to solve the problem. Any questions about that? Because now we're going to do it with a trajectory optimization. Question. Yes, Marco. Yep. So the question was, why did it not just set this to 0, 0 and find the local minimum of 0, 0? It's hard to say. My guess is that unless it starts exactly at 0, 0, let's start at 0, 0, This will probably tell us the same thing. The initial point is the best point. Oh, wait. For some reason, look, the short answer is I don't know exactly why it pushes it off there, because technically 0, 0 is within the constraints, right? It's viable. But for whatever reason, the optimization decided to push it more positively. Why exactly? I don't know. Because there's a lot going on under the hood when it's deciding which direction to go. Let's actually see a bit of what is happening under the hood, okay? So what we're going to set here, we're going to change some of the options. I recommend doing this, especially when you're new to optimization. You want to see what the optimization is trying to do. Let's set our options. Let's say optim options, okay? Okay? And we want to say, hey, our fmincon, we want to change our options. We want to change the display to iter. Okay? This will show all of the iterations. And then we go to our fmincon and we give it the final of its input arguments of options. And let's rerun it. Let's see what happens. When we rerun it, anytime now, here we go. Let me put a little semicolon after options, just because that's what outputs all that stuff. Okay, so here we go. It says iteration 0. It ran 3 functions. So basically what it did is, so anyway, it tells you how many times it runs your cost function. It said, at the first iteration, it runs 3 times. This is what the value of your cost function is. It says f of x. We mean j of w, right? And it says it's minus 9.81 after the first iteration. So it's already, for whatever reason, pushed it to some positive value and tells you, is it feasible? The closer it is to 0, the more feasible it is. Here it's exactly 0, so it's perfectly feasible. That's great. And that's for all your constraints, okay? And here it tells you your first order optimality. So this tells you, are your constraints satisfied? Yes. Yes, they are. This one tells you, are you at the bottom of your cost function? Is the gradient 0? And the closer this gets to 0, the better. And when it gets close enough, typically about 10 to the minus 6, and you can change that threshold, it says local minimum found that satisfies the constraints. Boom. Okay? All right. So let's get to our trajectory optimization. We've already set this up, thankfully, in our math here. So let's go back to our board and just power through, get this trajectory optimization going. We can do it in a half hour. I am 100% confident we can do it, barring crazy circumstances. All right. Question. We have a question? I heard someone pop in. Anyway. Okay. So. All right. So let's now make a new function. Let's call it. Let's make a new file. Oh, actually, you can't see it. I'm sorry. Let me pull it up here. Let's make a new file. We'll call it dragrace.m. Okay. Who wrote this? Me and all my friends, Christian Hubicki et al. Today in 2026-02-19, in the Common Era, this is a minimum time double integrator trajectory optimization. Okay. First, we're going to clear everything. CLC, clear. Close all. So that was a good question, Marco. I know the answer was, I don't know why. I can sort of speculate that if it ever pushes off of that 0, it might find a way to make it bigger. But the greater point is that there's a lot going on under the hood in the code for these optimizers, because we didn't write them, right? So they're a little bit of a mystery. Now, we can write our own. I hope to make a lot. Each year I keep saying, hey, let's write our own, and I get a little bit through it. That might be bonus material. Let's call this dragrace.m. Let's save it. Dragrace.m. Okay, and so we're going to want to run our fmincon. So we're going to want to be able to set up fmincon, where we have our cost function, our constraints. All right. So Let's look at our math again. So our cost function, if we have a decision vector, okay, that has 1, 2, 3, up through n values of u, and then that one, and one more value tf, our cost function is just the last element, right, of the decision vector. This actually makes our cost function super easy, friends. It is, we're going to say so we're going to define our cost function. Our cost is going to be at w. It's just a function handle that takes in w. You could put this in your own function file if you want, but this is way easier, right? And it's just the last value of w, right? It's the last one right there. Ooh, right? That's it. That's your cost function. Super easy. We're trying to minimize time. Okay. Now we get to the tricky part, which are our constraints. Okay, our nonlinear constraints. So let me save this and create a new function. I'm going to call it whole new function file. Hit Control N or Command N, whatever it is on your computer. Function. It's going to return our inequality constraint violation G and our equality constraint violation GEQ is equal to non-lcon. We'll call it non-lcon underscore drag race, because specifically for the drag race problem, and takes in W. Okay? That's what we're going to need. But in order to know, so let's write this out. We need our G values. So we have no inequality constraints here. We're going to make these bounds. Okay, let me make this a little bigger so you can see. Our nonlinear constraints here, they are equality constraints. See that? So we are not going to have any inequality constraints. That's just going to be an open, closed bracket, empty vector. We do have equality constraints. Let's write those out a little bit more specifically. They're going to be, if we're going to write this as GEQ of W is equal to 0, that means that we're going to need to have this S final back on the other side to make it equal to 0. So the way we can write this is that here's some vector S of T final minus, I'm going to try to write this in a better place. Okay, I'm sorry. I'm trying to find a place to put this. S minus S final and S dot at T final. These must all equal 0, the 0 vector. That makes sense? I just put that on the other side. And therefore, within this format of GQ is equal to 0, that means that this here, that's GEQ, right? So let's go back to our code. And you're like, oh, that's great. I know what TF is. I can write whatever S final is. I can say, hey, S final, I want it to go, S final, I want it to go, I don't know, 1 meter. It's a very short drag race. 1 meter. That's going to be our final position. We'll define it here. Our final position. Nice. And then we can say that, hey, G, we have no inequality constraints, so we're just going to say it's open, close. We have no inequality, nonlinear inequality constraints. We're going to put them in the bounds. Okay? And GEQ is going to be S at T final, which, how do we know that? The answer is we have to run a simulation to know that. But let's write that. We'll call it, so we're going to say this is S at T final. We're just going to put little blanks there. It's little underground blanks. We don't know what that is yet. Minus S final. And then the second one, we have S dot at TF, which we don't know what that is. Let's put a little underscore there. We don't know what that is. In order to get that, we need to simulate. sim, which means ODE 45. Okay, so this is where that's where we're now doing what we call the shooting, where we are simulating our problem to see if we got to the end or not. So we need to simulate. So we need to simulate our system in order to know if we have satisfied our constraints. All right. We'll call this one, I'll call this SF here, just so we have something there. And I'll call this DSF for, DSF final, right? Okay. That's what we're going to call our final velocity. So, which means we're going to have to simulate, and we're going to use ODE 45. Okay. Recall ODE 45. Help ODE 45. What do we need to tell it? We have to give it our ODE function that was in our state space form, which we've done many a time. We did it last lecture, okay? And we're going to have to give it a time span and an initial state, meaning where our system starts, starts at 0 position, starts at 0 velocity. That's different than an initial guess. An initial state is for a dynamical system, for state space. An initial guess is for optimization. That's the first guess the optimization tries to solve the problem. Okay? So they look similar, right? Y0, X0, but they mean different things. So let's really quickly write out our state space form. Okay? For drag race, I'm not going to drive it from scratch. We had our two states, we'll call it X, so X of t had our two states, S of t and S dot of t. So an X dot of t was equal to the derivative of each of them. Okay, S dot of t, S double dot of t is some function of our state X of t and U of t. And that function was S dot of t and 1 over m times U of t. It's not a dot product. I just want to do a little multiplication there. Okay, that's where m is your mass of the car. Okay, so this is what we called that's f of X of t and U of t. All right, so that's what we're going to set up. So those are our dynamics. So let's make a quick ODE function. Let's go back in the code. Let's make an actual whole new function file for our ODE function. Okay, I got to save nonlinear drag race. I forgot about that. So let's make a new function file for our ODE function. Okay. So ODE, so we're going to say function, and it's got to return. Just recall that what it returns is the derivative of your state. We'll call it dx is equal to ODE function, and it takes in the current time and state. This is what you did in your homework, right? Okay. So it's got to return the derivative of the state. Well, the good news is we have this written out pretty well right here, right? So here's the derivative of our state. So if we initialize our dx to be, so dx would be our first element, S dot, which is one of our states. In fact, it's our second state, x2, semicolon. And now we have 1 over m. We have not defined m, but we will here. Okay, 1 over m times U of t, which we have not defined U or M yet. Okay? We define U and M, we're in good shape. We have ODE 45. All done. Okay? So let's get M. Let's define the mass of our car. M in kilograms. Okay? So, awesome. Now our U, that's a little trickier. What is U? Well, our U, I'm going to scroll up here. You'll recall we get from this spline. The spline is back in action. If we know what time we're at, you see my little red line there, then we can figure out what control input U we're applying at that time by interpolating, like you've done on your homework, along that spline. So we're going to do an interpolation. But it requires us knowing this list of U's and the final time TF. Okay, so hold on to that. So let's assume for a moment, because right now in this code, we don't have access to the current decision vector W, which would tell us these U's and this TF. But we're going to find a way to pass it into this function here, okay? W. This is the trickiest part of all this, okay? That we're going to have our constraint function. This is our nonlinear constraints, which takes in W. And we're going to have to take that W and pass it into our ODE function. So that way our ODE function knows what force to apply, okay? So let's assume we have a way to do that. We will. Okay, it's just a little bit tricky. We have to do a little bit of a function overload thing. That's not the right word. We have to pass in extra parameters. So let me save this as ODE function. Okay. U. So U is equal to, we're going to interpolate that. So what do we have to interpolate along? Okay, it's the interpolation function. Interp1, help, interp1. We're going to take in a list of the horizontal points. That would be the horizontal position of that, you know, the horizontal position of them. Then a list of all the vertical positions of these points. And then the time we want to actually interpolate at. Is it this time? Therefore, we want to know that. Is it this time? Therefore, we want to know that. Okay. That's the current time, which we do know. Up here in the code, that's T. It'll tell us the time. So we need a time list. We need a U list and the current time. I'm just calling them U list and T list. So what is T list? Well, T list is a list of all these time points that align with these points here, right? They're evenly spaced. So if we know what TF is, and we know how many U's there are, in this case, N, we can create a list of time points, 0, whatever that is, whatever that is, whatever that is, whatever that is, up to TF. And for that, we'll use the linspace command, linspace. So we're going to linspace between 0 and the final time, TF. What is that? Well, we know that from the decision vector W. It's the last element. So we'll call that TF, and right above it, we'll say, hey, TF, that's the last value of W. So get the final time. Okay, and how many points? N. Well, what's N? Well, N is the size of this vector. How many elements are in that vector? Minus this one, right? That last one's not part of N. To see that, this is not complicated, hopefully. But are you following? If we know what N is, so N is the number of elements in W minus 1. 1, 2, 3, let's say there's 10, N equals 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There would have been an 11th element. So if we say num_L of W, it would say 11, subtract 1, get 10. So if we ever change N, automatically this code updates to whatever that N is, right? Pretty neat. Okay. Moving on. So we have N, we have TF, we've defined T list with a semicolon. So let's say get the number of input points N. And then we're going to say define the time points on the spline and U list. Okay? What are the list of U's? Well, it's all of these values in the decision vector, except the last one. So W, our decision vector, we want all the values except the last one. 1, end minus 1. So you want to get the control input points. Okay. Awesome. Well, actually, we were defining everything right here. Okay. Then here we are interpolating. I put a semicolon there as well. Interpolating the control input at the current time. Okay. This is all just to get this U right here. Okay. Here we are defining the derivative of the state with respect to time. That's our ODE function. Okay. All this stuff, this rigmarole here, that's how we're encoding the fact that we have a little spline, right? So now we can call ODE function. We can send in our current time, our current state, and the decision vector. Okay? So let's go back, my friends, to the non-LCON. This is where we are simulating our system, right? Okay? This is the last little tricky bit. So we're going to say, because we need to know what the final position and the final state are, right? Okay, in fact, what I'm going to do is I'm going to show the fact that to show how this all works, I'm going to create a new simulation command, okay? Watch this. I'm going to say create a new function. I'm going to create a new function. I'm going to call it. It's going to right now it's going to return nothing. I'm going to call it simulate drag race. Okay. Now, in order to simulate the drag race, I'm going to send in just the decision vector W. Okay. So this is going to simulate the drag race. It's going to run ODE 4.5 for us. Okay. So simulate drag race. I'm going to show you that this all works, this simulation that we have set up. Okay. So takes in W. Now we're going to run ODE 4.5. Okay. And we're going to get out the time outs and the X outs, just like we've done when we simulated code before. It sends us all the time vector that it simulates, all the states along the way that it simulates. Okay. ODE 4.5. And we got to give it the ODE function, which we call ODE fun. Okay. The time span. Okay. What is the time span? Well, the time span is a vector. We start at 0 time. We want to end at our final time, T final. Well, what is T final? Well, T final is the last element of our decision vector. T final. It's equal to W end. So T final. Okay. So the last element of the decision vector, send into the decision vector, and then it's going to simulate the system for us. So great. ODE function now requires our time span, T span. It also requires our initial state. It calls Y0. We'll call it X0. Our initial state, we have 2 states. Initial position starts at 0. Initial velocity starts at rest, 0. Okay. Initial state. This is our time span. Okay. Here we're getting our final time. So there we go. Now we got to give it X0. Done. So here's what I'm going to do. I'm going to plot what happens. I'm going to plot X out, T out, and X out. I'm going to want to plot the position over time. So that's the first state. So colon, comma, 1. Okay, there. All right. X label. Time in seconds. And Y label is going to be car position in meters. So we're going to send in some decision vector, and this should hopefully simulate the system. There's going to be an error, just a little spoiler, okay? Okay, simulate drag race. So simulate drag race. Okay, I'm going to give it a decision vector, which has a bunch of u's in it. Right now, I'll just make them zeros. I'm saying 0, 0, 0. I don't think it matters that it's a row vector, but let's just, so let's ignore it for now. And a t final, so it simulates for some time at 1, okay? Here, clearly, I gave it 3 elements and then an extra one, so it's going to know that n equals 3, okay? And let's see what happens. Error. Not enough input arguments. Here we go. Not enough input arguments into the ODE function. This is the problem that we talked about, where it's expecting a third input argument into ODE function, W. But when ODE45 is calling ODE function, all it's expecting to send in, all it's going to send in on its own, sorry, ODE45, all that ODE45 is expecting to send in to ODE function is t and t, your time and your state. So we have to tell it to send in your decision vector too. So how do we do that? This is cool. We say we're going to create an inline function that says, hey, we're going to call this ODE2, all right? And its only job is that whenever it's called and you send in your time and your state, the thing that ODE45 is expected to send in, we hijack it and we say, let's send, actually, when you call ODE2, and let's change this to ODE2. Actually, I should have included the at symbol as well as another problem. ODE2. What it actually calls is ODE function with that time, with that state, and let's send in W. We have access to W. Let's smuggle it in. Okay? All right. So whenever ODE2 is called, it also sends in W to ODE fun. All right. Now let's try simulating the drag race. Okay. I'm simulating the drag race. Hopefully it works. Let's see what happens. I'm just rerunning the simulate drag race 0001. Let me get rid of that stuff up there. For some reason, it's taking a while to show up the figure, but... And I don't know if you can see that, but it's just a flat line, which makes sense. We didn't send in any force. We're starting at rest, and our forces are all 0, 0, 0. Let me make them 0, 0, 10. Sorry, let's go, let's run this again, sorry. And 0, 0, 10. So this would be flat, flat, 0, and then up to 10. So it should do something, right? Let's run it. Okay, I gotta close everything, close all. So you can see it pop up. Here we go. Does nothing, 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 then essentially starts accelerating. You see that? Hopefully you can see that a little bit on, yeah, you can see that a little bit, right? So, great. We now have the ability to simulate a problem. In fact, let's use this function that we just made, okay? And let's have it send back the things we need in our constraints. What do we need to know? The final position, the final speed, and just use this simulation function we just made. So, with that, let's send back SF and DSF from our simulation function. Okay? Right now, let's comment out this plotting, because it's going to be called over and over and over again. Every single time a new decision vector is tried by the optimizer, it will call this function. So we don't want to keep plotting. We can add that at the end, though. Okay? So, all right. So that means SF, our final position, that is X out, and that's the very last row of the first column, the very last position. And DSF, that's our second state, our velocity is X out, the very last row of our X out second column, because it's our second state. Okay? So now simulate drag race sends back that. So let's go into our non-alcon for the drag race. Drag race. All right? And we're going to say, hey, SF and DSF are equal to simulate drag race, and we send in our decision vector, W, into our constraints. Look at that. Nifty, neato, cool. Let's go back. So now we have our nonlinear constraints. Notice that all that complexity for that was the fact that in order to figure out if our constraints work, we had to do a simulation. Okay. Let's try to push this out to the end. Let's go to our drag race.m. We have our, and we're going to start, we're going to run fmincon. Okay. So our W star. So what do we need to know? We're going to need to know our cost function. We need our W0, which is our initial guess for the optimization. This is in our drag race.m. All right. So W0, our initial guess. We're going to have it be, so we have n points. Let's just say n equals 10 points. So we're going to say it's zeros, n comma 1. So it's a bunch of zeros in a vector, okay? And then some initial guess for our time. Let's just say 1 second, okay? All right, that's our initial guess. So it's a bunch of zeros and 1. All right, so what else do we need to know? So we're going to say W star is equal to fmincon. Fmincon, these are a cost function. It's already called cost. Our initial guess, W0. Our A matrix, we're not doing linear constraints. B matrix, not linear constraints. AEQ, BEQ. Now, lower bound and upper bound we're going to need, okay? So our lower bound, okay? Keep in mind that we have some fmin and some fmax, okay? Let's say fmin is equal to minus 10. Fmax is equal to 10. And we want to make sure that none of those force points are above or below those points. So our lower bounds is going to be a bunch of minus 10s, okay? Where our LB is going to, well, so we'll say that it's a bunch of 1s of size n by 1 times fmin. So it's going to be 1 times minus 10, right? Okay, this is a little quick. I apologize. And the minimum time, we don't want to go backwards in time. Thank you very much. So the minimum time, I'm going to have it be 0. The lower bound on time. That's the last element, okay? Now, the upper bound, we're going to do the same thing. We're going to copy it. And it's going to be fmax for the upper bound UB. And the upper bound on time, there's no upper bound on time that we want to put in there. Infinity. So let's see. This should be A, B, A, Q, B, Q. I think we need a lower bound. So there should be 4 open close. This should be LB. And this is UB. And we need non-LCon. So we're going to say at non-LCon drag race. That is our function handle for non-LCon. Let's do optim options, so let's say options here. And we'll say options is equal to optim options. We're going to say that fmincon, we want to turn on the display iterations. That's important. So we're going to say display. I'm doing tab complete to make this quicker, and iterations. Okay, I'm going to have to go soon. Okay, so that iterations semicolon. So we're running fmincon. Let's see what happens, friends. Okay, I think I screwed up some code. Oh, yes, this should be a semicolon here for the W0. Because I made a column vector and I was trying to add on another row to the column. So it should be a semicolon, not a comma. Oh, it's running. It's running. It's running. It's doing something, friends. Whoa, is anyone getting that? Local minimum found that satisfies the constraints. Notice it took a little longer, right? The code was running a little longer. Anyone getting that? I see at least one thumb up. I'm going to put this code in the chat so you can all copy that in case you need it. That was all the stuff above fmincon. Here's the stuff in fmincon if you need to put that in there. See if you get it, if you need to compare. Okay, so what happened? This is pretty cool. Local minimum found that satisfies the constraints. That's great. We did it. What was the W star, the optimal value of every decision vector? Well, 10, 10, 10, 10, almost 10. minus 10 almost, minus 10, minus 10, minus 10, minus 10. And the last value, 0.63. The minimum time it found to get to the end was 0.63 seconds. And what does this look like on your, for your spline? I'm just going down to the bottom of my notes here. What does that look like, the solution? Looks like this. Time, U of t. Here's 0. Here's the maximum. Here's the minimum. It looks like that. That was the bang bang. Let's just plot the first 10 points of that. I'm just going to say, hey, friends, let's plot. Let's close all. I'm just going to show you the plot of W star, the first, all the values but the last one, 1 n L minus n minus 1 there, just to show what the points look like. What did I get that wrong? 1 n minus 1 W star. Oh, W star with no. Right. Let's plot it. You can't really see it, but it's high and then it's low. Bang, bang. It got the right answer. Okay? Pretty cool, right? Trajectory optimization from scratch. It got the bang, bang solution. All right, I got to go. I got to run to my next meeting. Okay? So I'm going to pop off now. This was fun for me. So that's what we called single shooting, because every time we wanted to simulate the problem, we simulated the whole problem. Look back, we talked about something called multiple shooting, which is going to be better for unstable systems. It's going to be less sensitive to initial guesses. This actually worked really nicely. So with that, I'll happily take some questions while I pack up. Everyone take care.